I will use ChatGPT Study and Learn to understand the best advancement in last 3 years in AI, which is this Muon optimizer that cut training of neural networks by half. So these few people just doubled AI progress single-handedly. Because when you make improvements to optimizer, you are literally making improvements in how AI learns, which is the root, the base, the foundation of entire AI, entire field. So I will start with this singular value decomposition. So when we are updating AI weights, neural network weights, we want to update them so they improve the loss. The loss goes down, the error goes down. But we don't want to change weights too much because that could lead to instability. Because we can calculate how loss goes down in this particular place we are at. But if we jump too much in the weights, then it's gonna be dark. We're gonna be jumping in the dark. So we wanna just improve the loss, but not jump too much in the weights and in the loss function, because we just see it locally. So we have some linear layer. Output is weights multiplied with input, and we have loss, and then we have gradient of loss with respect to weights. So how does loss change as we change weights? So we need this to be able to we want to choose an update for weights that minimizes this is the dot product of the gradient and the change in weights. So what this means is just that our gradient will show how to go up the loss function. So we want to go in the opposite direction. We want to go down when we change the weights. So gradient will show how to change weights to go up, and we want to change weights to go down. So that's why we minimize. So we put a negative value here, the biggest negative value in this dot product. But as I said, another constraint we have is that change in weights must not be too big. So we need to bound it, constrain it. To understand this better, let's see. So we have the output is equal to weights times input. So if we change the weight a little bit, we have change in the output as well. And it's done in this way. So it's going to change by delta W times X input. So the delta, the delta of the output, change of the output is delta W times X. So we also have this constraint, only update weights in a way that keeps changing Y, changing output small, because big change, it's gonna be unpredictable. As I said, gradient will show us how the loss will change if we add small amount to the weight. The more we add to the weight, the more it's traveling away from this gradient spot, so we don't know what it's gonna, what the function is there. So let's check out this equation. This norm tells us the maximum amount that delta W can stretch an input vector on average. So we are saying let's only allow updates delta W that don't stretch input too much on average. So here we are working with theoretical inputs. So what is the worst case change delta W could cause? No matter what input vectors you give it, as long as the input has RMS norm 1. So for now we can just omit this RMS norm thing. Let's just talk about this. So we have this delta W, it's like a matrix update, or it's a matrix, and it's gonna multiply X, so it's gonna stretch X in some direction, so rotate or reflect. So we want to find which X, theoretical X, what could be this set of numbers, the matrix X, that's gonna get stretched most. So it's gonna have experienced the highest change for this particular W that we are testing for. So we need to find this X that's gonna get stretched most. So we are checking over all possible unit RMS X inputs. So unit RMS is one value of the RMS norm. So what is this RMS one of the vector? It means that each of the dimensions of the vector x, y, z on average has length 1. So that not the dimension of the vector, but not the length of the vector, but the length of each dimension of each number in the vector. So our goal is to constrain the delta, the weight, so that no input vector that has average dimension length 1 gets stretched into an output vector with average dimension length a lot bigger than 1. This controls the average output change, so the average change of the y output, not individual dimensions. So we are taking the average of all of the dimensions. So we're not focused on individual coordinates being stretched. We care about the average output, so we care about average stretch per coordinate for every coordinate. So even if one coordinate explodes and becomes huge, if there are other coordinates that shrink or become smaller or balance somehow this stretch, then that's okay, because the average is still not too big, the average stretch per coordinate of the x input vector. So we add this constraint for the training stability. Also, we use this to connect input and output space, so we can measure how input influences output. So for which inputs and vectors output changes most and how does it change. This way we can make sure to know the worst case scenario and to make the update safe for all inputs. So let's recall our optimization formula. So we want to minimize the dot product between the gradient that points up the loss and the delta weight that points down the loss, because they must be opposite. But the delta weight is subject to not changing the output too much, the RMS of the output, which is average length of each dimension of the output vector or output matrix. So let's see what a singular value decomposition is. So let's say we have this matrix G, which is m times n. So it's just gonna take some point x, point in space, and stretch, rotate, and flip the point. Any such matrix operation can be broken into 3 steps. Rotate the input, that's the V transpose. Stretch along specific axes, that's the sigma, and rotate the result, that's the U. So any matrix can be decomposed into these 3 matrices. So first rotate input, and then stretch, and then rotate the stretched thing as well. So these are called, so the V is right singular vector, sigma is diagonal matrix of singular values, and U is the left singular vector. So first rotate input vector into a special frame via this V transposed. Second, stretch and shrink along the axis of that frame. And third, rotate again into the output space, after this is stretched. So the sigma, the stretching matrix, looks like this. It has all the zeros except these sigma values, which are singular values. So each of these is gonna stretch a single dimension. When you multiply some vector with this diagonal matrix, you can check, you will see that each of these rows or columns, however you do the multiplication, it's gonna be the same. It will just stretch that dimension that it corresponds to. So this is gonna stretch x dimension, this is y, z, etc. So why do we need 2 rotations? Because we first rotate, then stretch, then rotate again. Because the stretch is done along in the certain axis, in the certain coordinate system. So we first need to rotate to that coordinate system. So the whole 3 matrices do the following. Take some input, rotate it to a special coordinate system, stretch it along those axes, rotate the result somewhere else. So let's say the input is circle and G is gonna turn the circle into ellipse. So this rotation or stretching of the circle can be decomposed into three matrices, three singular value decomposition matrices. First, we will rotate the circle so this stretch aligns with the x and y axis. It can be like this, so this can go down, this can go up, or both can get stretched. And then we will stretch in those directions and then rotate into the final orientation. So this can be like the back as it was, or it can be different orientation. So let's say we have this matrix. So how do we get these three matrices? So we'll explain the process first, but let's see what we want to get. So we can start from this middle matrix. So it's gonna stretch x of whatever this G is multiplying by 3.26 and y by 1.54. Okay, this U rotation, so the first is this will rotate the x first, then this will stretch, then this will rotate lastly. So this is simple matrix rotation. So you can check this at 3 blue 1 brown, how matrices rotate space, and pull all of the vectors and dots and points and shapes in the space. So the way we will get these is we will first compute G transpose times G and find eigenvectors and eigenvalues of that new matrix. These give V and sigma, and then compute U after. So some intuition behind this. If you have a circle and you apply this A matrix, multiply with A matrix, and then you multiply the result of the transposed A matrix, you will get a new shape of the original space. So the final shape shows which directions got stretched the most along axis of the ellipse, because now it's ellipse, it was circle before. Which directions are safe or squashed, short axis. And here the cool part, the eigenvectors of this multiplied matrices point in the input directions that are stretched or squashed the most by A. So if you turn this into like ellipse, eigenvectors will point in the ellipse coordinates. So A transpose times A is stretch detector in input space. So how much does it stretch the circle or X or whatever? So how does this all connect back to our Muon optimizer? So remember, we want to find change in weights that goes in the direction of the gradient. This should say opposite of the direction of the gradient. I don't know if ChatGPT messed up a little bit. And then respects this constraint, so the update is not too big. Step 2 is to use singular value decomposition to align or process this gradient in a different way. So we will decompose gradient into these three matrices, and we want to exclude this stretching matrix because this is uncontrolled and we want to stretch just with some small value epsilon. Is this epsilon? And we don't want to stretch with this. So we will remove this. We will just have U and V transposed, which is rotations. So we are okay with rotations. And these matrices are orthogonal because they are just rotations, which means their rows are normal to each other. It's just a bit of facts. So when I say rows of a matrix are normal to each other, means if you take a vector, a row, and you plot it as if it was a vector, and you take second row and plot as if it was a vector, you will have 90 degrees angles between them. That's what orthogonal matrix is, and that matrix will just rotate whatever the space you are multiplying it with. It will not stretch. So we will use the same U and V but get rid of the sigma, and we will replace sigma with this epsilon. So basically, instead of having a learning rate times sigma, we will just have this epsilon, which is a hard constraint on how much we want to stretch. So what that will cause is after the stretch, so it will stretch. So we will no longer have like one RMS will no longer be one, it will be stretched, it will be more. I'm not sure if it can also be squished or not, I'm not sure. So this update can stretch inputs of RMS1 to outputs of RMS epsilon, whatever it is. So the average length of dimensions in the input is 1, but in the output it can be epsilon. So the operator norm measures how much the matrix can stretch an input vector in RMS terms. So these rotation matrices, they don't stretch, so their operator norm is 1 here, but when you also multiply that with this epsilon, then operator norm is epsilon, so the stretch is now epsilon. And guys, I've been reading it correctly, so it's good. How to read this epsilon, okay. So the main point here is we are replacing sigma times learning rate with this epsilon, because original singular values in that sigma matrix can vary a lot. So we just replace all of them with epsilon. So now epsilon acts as a uniform step size controlling the maximum allowed stretch on the output. Because as I said, we don't want to change the update matrix. We don't want to make it too big so the weights get changed a lot. We want to limit how much the weights get changed. So we want to limit the magnitude, the size of the update matrix. So what we've concluded is singular value decomposition. We would just rotate the matrix and we would limit how much it changes the output, or the epsilon, the stretch, so it's not too much. And we just need to control the stretch because the rotation will not amplify and make training unstable. We just need to make sure that gradients don't stretch weights too much, because gradients can be large not only because changing weights in this direction would decrease the loss, but also because if weights multiply some big, arbitrarily big input number, which is just arbitrarily chosen, then that weight will have high gradient, high influence onto the loss, onto the output, sorry. So the gradient there would be large just because the weight multiplies some large number, not because it would reduce the loss most. So why do we need to control length? Unstable activations, if weight update stretches inputs a lot, the output activations can become very large. Exploding gradients during backpropagation. This can happen if input is too large or learning rate is too large. And then these activation functions can output maximum huge values or be saturated or very small values. And then there can also be nonce or infinity. So that's why we need to control the raw magnitude of the weights of the vectors. We want to keep them around 1 or between 0 and 1 or minus 1 and 1. But computing singular value decomposition is computationally expensive and slow. Muon needs a fast way to orthogonalize the gradient matrix G without full singular value decomposition. So first of all, for a symmetric positive definite matrix where A matrix is equal to A transpose, the singular value decomposition simplifies to the eigendecomposition with Q lambda Q transpose, where Q is orthonormal eigenvectors, which is same U and V, and lambda is diagonal matrix of positive eigenvalues. So as I said, singular value decomposition is too computationally expensive and slow, so we want to actually do it like this. So in order to orthogonalize gradients, we will compute this. So G times 1 over square root of G transpose times G. It's a bit tough, but this is how we can calculate the orthonormalized orthogonalized version of gradients, where each row is normal to each other row, if you look at rows as vectors. So we want to approximate this with this Newton-Schulz method. We don't even need to have it 100% correct value, because neural networks can deal with a bit of approximation. So we initialize matrices x0 and y0 as starting guesses. And then we repeat some operations, and as we repeat those operations, the xk matrix, this one, xk, moves towards inverse square root of a of what we need, like g or whatever. So we will do maybe 5 to 10 these operations, whatever they are. We will explain them, and we will get approximate value. So instead of SVD, Muon applies Newton-Schulz iterations to approximate the orthogonalization. So you see orthogonalize g and then apply with this stretch factor epsilon. And this can be done with matrix multiplication, which is fast and good for GPUs and parallelizable, this Newton-Schulz method. The first step in Newton-Schulz is to calculate this gradient transpose times gradient matrix. So that's going to be our A matrix. So A matrix will be symmetric, same values across diagonal, and positive definite matrix, which means when you take any vector x except the zero vector that has all zeros and apply this transformation that's symmetric and positive definite, in a way x, so the input transposed times this matrix, positive definite symmetric matrix times x, you get positive number, which is just a single number. So when you take a vector x, multiply by matrix A, and then multiply by x transpose, you get a single number, because ax gives you a new vector, and then multiply that with x transposed, it's gonna be a dot product. So after we calculate this A, which is gradients times gradient transposed, then we normalize A with this Frobenius norm. So this norm will make it so that sum of squares of all elements in matrix is 1. So this will just normalize. If we have big values, we will push them back. Just you can understand it as that. So if we have a matrix, we're gonna do it like this. We're gonna calculate this Euclidean distance of entire matrix, and then we will divide. So we get these kind of normalized values, and we can check that it correctly adds up these squares to 1. So Newton-Schulz is polynomial approximation, so it's using polynomial to approximate this function. And polynomials are easier to compute, so we will use them. And you can use polynomials to approximate different functions. For example, like this, you have this function you can approximate. You see here, for example, in some region, it can have very similar values, the polynomial and the function it's approximating. So if you check the code here, we have ABC variables that are hard-coded. These are coefficients. So this is the function that we are approximating. It's this one, I should say. So we have ABC values. We have I identity matrix, just because this is with matrices, so we want to stretch this A to identity matrix. And this A is x times x transposed, and x is our update of weights, update matrix. So we want to make the update matrix orthonormal, so orthogonal rows and normalized, as I was explaining. So this is the polynomial, and we use this polynomial to approximate that function that I was explaining. So the coefficients are chosen to converge fast and stably towards the inverse square root. So we want this polynomial to approximate this function. on the interval of eigenvalues 0 to 1, including 1, since A is normalized. Not sure what this means. Okay. You know, we have applied normalization to the entire, so I guess the values in the matrix will be less than 1, between 0 and 1. So each iteration will basically push x transpose to identity matrix. Identity matrix is the measure of orthogonality. So if it's identity matrix, then it's perfectly orthogonal. So if this is true, then x is orthonormal. So rows of x are orthonormal. They have length 1 normalized and mutually perpendicular. If you look at each row as a vector in a space, in space. So basically we want to just change the update to be rotation, not to have stretch. And we will apply stretch later. Epsilon is multiplying this Newton-Schulz transformed matrix. I think that's gonna be it for this video. You can check this blog post and see you next time. I will be explaining this even more, I think, next time. So see you next time. And you can check my other videos here.